Hi everyone, my name is Firas Abuzaid, a sixth-year PhD student at Stanford. In this video, I'll be discussing some recent work on traffic engineering for wide area networks. This work was completed at Microsoft Research. Traffic engineering is a classical problem that has been around since the advent of networking. In our setting, we're given as input a wide area network topology and a traffic matrix, which represents the traffic demands on the network at a given point in time. These TMs arrive periodically on a regular basis. Both of these inputs are fed into a traffic engineering solver, which outputs flow allocations on the WAN. Now, the current approach applied today is to compute the flows by optimizing a linear program, shown here. And the runtime to solve this linear program scales quadratically with the network size. Note the log-log scale for the plot in the bottom right-hand corner. Now, the problem is data center WANs have steadily grown larger and larger over the last decade. 10 years ago, we saw software-controlled WANs with only a few sites and links. But now, Microsoft is projecting WANs with potentially thousands of sites and links in the next few years. So naturally, this is going to lead to longer and longer runtimes for traffic engineering. Slow traffic engineering is problematic because it leads to underutilization on the network as demands change. To see this, let's take a very simple topology. Two nodes sharing a common link to a third node, and the link has 20 units of capacity. Now, suppose a traffic matrix arrives that requests 10 units of flow from node A to C, and 10 also from B to C. Note that no other traffic is requested. The TE solver will use that matrix as its input to compute a flow allocation. Then, 5 minutes later, a second traffic matrix arrives, and it requests 15 units of flow from A to C and 5 from B to C. Unfortunately, the TE solver is unable to respond in time. It allocates based off of TM1 when TM2 is what's needed. This leads to 10 units sent from A to C, even though 15 were requested, and 5 units sent from B to C, which gives us a total utilization of 75% instead of 100%. This toy example is not contrived. When analyzing the traffic patterns on the Microsoft Azure WAN, we see significant changes in traffic over time, and this leads to consistent underutilization on the network. And link failures in the network make this problem even worse, since TE operators typically keep utilization low in order to anticipate failures and still maintain high availability. A second and related challenge is that larger WANs also lead to more forwarding entries, or fib entries, per site. To see this, let's look at the simple topology of 6 sites and 8 links in the continental United States. At a single site, say in Seattle, we can see that a fib entry is required for each path that passes through the site for each commodity in the WAN. The number of fib entries at this site is therefore proportional to the number of sites times the number of paths times the average path length. So therefore, the total number of fib entries is proportional to the number of sites squared times the number of paths times the average path length. So what happens when we double our network size, say to 12 sites and 18 links? Well, the number of fib entries starts to blow up. It also scales quadratically with the number of sites in the WAN. More fib entries requires more ternary content addressable memory, or TCAM, which ultimately leads to higher costs. So in this talk, I'll show you how we scale traffic engineering to large data center WANs using a technique we call NC flow, or network contractions for flow problems. The key insight undergirding our work is that data centers and traffic are not uniformly distributed. They're clustered. As the WAN evolves and grows in size, there's a natural clustering that occurs because data centers are often built close to large population centers, and traffic is steered towards those nearby data centers. Let me show you an example of what this clustering translates to in reality. Suppose we take this WAN of the continental US and we partition it into these two clusters, orange for the West Coast and green for the East Coast. If the traffic on this WAN were to follow a uniform distribution, it would look something like this. And notice that we've grouped the rows and columns of the traffic matrix by our two clusters. However, when we analyze the traffic patterns on the Azure WAN, we observe that it actually resembles something closer to this distribution. Both the traffic and the link capacities are actually highly concentrated within the clusters. But a clustering isn't just handed to us. We have to find it. And we want to find a good clustering, i.e. one that yields more demand and capacity within the clusters. There's also this question of how many clusters we should use. And in our experiments, we observed that roughly square root of n, where n is the number of sites, typically captured a good trade-off between speed and complexity. Moreover, we found that computing a good clustering is actually quite tractable. We can use standard clustering algorithms combined with a simple grid search to find a good clustering with minimal runtime overheads. And you can find more details of that in our paper. So once we have these clusters, how do we leverage them to solve TE more efficiently? Well, we have to solve the flow problem between clusters. Now, this could lead to a highly complex flow problem still. Clustering alone doesn't reduce the number of variables in that linear program we first saw. But we can use the clusters to bundle demands. What do I mean by demand bundling exactly? Well, let's take our traffic matrix from the previous slide. And since we're only solving the inter-cluster problem, we're going to ignore the intra-cluster demands. What we then do is take the inter-demands and bundle them into a single aggregated demand on an aggregated graph, which gives us a significantly simpler flow problem to solve. But we're not done. We also have to solve the flow problem per cluster. We have to allocate flow within the cluster. But because we've solved the high-level flow problem in the previous slide, we can now treat each cluster as independent and solve each of these smaller per-cluster problems in parallel. This is especially true once we apply not just one or two, but many clusters, such as square root of n. Let me show you what I mean. Again, we have our original traffic matrix, and now we're going to look at the intra-cluster traffic. For the Orange West Coast cluster, we can solve this independent subproblem, and we can bundle demands flowing to and from the East Coast. Similarly, we can do the same thing for the green East Coast cluster and bundle demands to and from the West Coast. Again, this leads to a significantly smaller set of flow problems compared to the original one, and we can solve these subproblems in parallel. It turns out that clustering and bundling also reduces the number of fib entries in the network. If you recall from the beginning, the number of fib entries scales super linearly with the network size. But if we cluster and bundle, we can eliminate the fib entries required for sites outside of the cluster, and instead replace them with a single entry per cluster. This gives us a much more scalable solution. Now, there's one final concern that we should discuss. Recall our topology with the West and East Coast clusters and the aggregated graph that we generated from that clustering. There's one detail I glossed over. What exactly does that single link in the aggregated graph represent? Is it the top link in the original WAN? Is it the bottom link, the middle link? This question is crucial because the ideal answer is that it's all three links bundled together. That way, when we solve the per cluster subproblems, we don't have any link capacities in the WAN that go to waste. But what if the two clusters don't pick the same link for a given demand? In that case, the flow for that demand won't be allocated at all. So to eliminate this potential conflict, we select from the clustered network a single link per cluster neighbors for every pair of clusters. Then we solve the problem with those link assignments. And this increases the link capacity used between clusters while also ensuring that no conflicts arise. Now, it is still possible that the link assignments we select lead to a bottleneck that could have been avoided with a different selection. So to account for that, we apply an iterative approach and shuffle the link assignments with each iteration. The best way to understand this is through an example. Here we have three clusters, A, B, and C, connected in a chain with two intercluster links between each. In the first iteration, we'll assign A to B flows on the left and B to A flows on the right. The same goes for B to C and C to B, respectively. Finally, we assign C to A on both intercluster links on the left and A to C on both intercluster links on the right. After that, we run our first iteration of the algorithm and allocate flows on all of these links. After that first iteration, there's some residual capacity and some residual demand. So now we'll assign A to B flows on the right and B to A flows on the left. We flip them. The same goes for B to C and C to B. And of course, we'll also flip the assignments for C to A and A to C. We run our algorithm again and allocate the remaining residual flows on the residual capacities. Now, to be clear, this particular step is the most nuanced part of NC flow, and this is by no means the only way to resolve this reconciliation issue. We do discuss alternatives in the paper, but suffice it to say, we found that this solution is effective both in its implementation and its empirical performance. So to recap NC flow, we contract the network into clusters and then solve a smaller set of flow problems on the clustered network using the pseudocode below. The solution details are in our paper, of course, but we want to highlight some important properties. NC flow is always feasible, which we prove in our paper. It leads to faster runtimes, and it can allocate flow optimally under certain conditions, which we also prove. Furthermore, we show some counterexamples where NC flow can perform suboptimally, but also demonstrate good performance in a wide range of empirical conditions. So I'll briefly discuss those results right now, and then we'll conclude. To evaluate NC flow, we benchmarked against a standard implementation of the multi-commodity maximum flow linear program, which we outlined in the very first slide. We also compared against several prior works on traffic engineering, such as SMORE, as well as combinatorial algorithms such as Fleischer's. And for failure handling, we evaluated NC flow against TAVAR. Unlike these prior techniques, NC flow is the only approach that exploits clustering to decompose the problem into a more tractable form. In our experiments, we found that across a variety of public and private topologies, on both synthetic and real-world traffic, NC flow allocated 98% of the optimal total flow in the median case, but was 8 times faster in the median case too. Moreover, we saw maximum speedups of 1300x. As you can see in the bottom right plot, NC flow is orders of magnitude faster than the standard linear program, as well as other state-of-the-art approaches. NC flow also achieved 6x fewer fib entries and a 25% improvement in utilization, because we were able to more quickly respond to changes in traffic demand. Lastly, we evaluated NC flow in the context of handling link failures, and we found that compared to TAVAR, NC flow was able to carry more flow before and after failures, and was able to recompute flows in response to failures within 10 milliseconds. To conclude, NC flow is an approach we developed at Microsoft to scale traffic engineering to large data center WANs. By dividing the WAN into clusters, we can then solve a smaller complexity flow problem that gives us faster runtimes and fewer fib entries at the cost of a very small amount of flow. Prior work has tried to decompose flow problems before, but we are the first to achieve sizable runtime improvements and fib reductions. NC flow represents a novel real-world solution to a classic optimization problem, multi-commodity maximum flow. And we believe it has broad applications, not just in traffic engineering, but to other problem areas where capacities and demands are clustered. Lastly, we have made our code and our technical report publicly available on GitHub, and we encourage you to check it out. You can also reach out to us at this email address if you have any questions. Thank you for your time.